Okay, so welcome everybody to part two of this seminar on entropy, the concept of entropy. Let's see if I can write the word. I can. In which, so I did post a link to the notes that I put together when preparing for this on the SLT channel in Discord. So you can feel free to grab those and kind of follow along, look ahead, catch my mistakes or my hesitations or whatever, as I try to recall them, because it was a while ago now. In the first, the overall thrust of this endeavor right now is to get a conceptual feel, build kind of intuitive muscle for the concept of entropy, and come at it in two ways. One is the information theoretic view, and the other is the physical view, the physics thing, entropy. And the first session, we basically got through the information theory part. And so this remaining 54 minutes is going to be focusing on the physical viewpoint, but really trying to make the point that they aren't so different after all. So just to briefly recap what we said last time, I said if you have a discrete probability distribution such that the probability of the ith outcome is pi, then the information content of observing that your system has resulted in the ith outcome is well described by the logarithm of 1 over that probability. And the 1 over p part kind of says that you learn more, or when you observe, that's when the outcome is what usually happens, then you haven't learnt as much as when you're surprised. It's like last time we had a game of submarine, which is a little bit like battleships, and if you happen to guess straight away where the opponent's battleship is or submarine is, then you've learned a whole lot. You've determined where it is. And there's only one of them. There are many more empty squares on the board. And so if you miss, then, well, you haven't learned quite so much. You've just eliminated that one square. And then the log achieves additivity, right? The idea that the information conveyed by like a compound event with probability pi qj is the sum of hi and the hj, if you like, or the information, it's the sum of the inverse of those two probabilities. And I'm just, so far, that's just a kind of proposal for the definition of the concept of information. And it makes sense, it makes intuitive sense in those two ways. But it lets us write down the average or expected information content of this discrete probability distribution, which of course is this, when you substitute for hi. And we then looked at Shannon's axioms and Shannon's derivation of that formula, which kind of puts it on a more rigorous footing. Okay, so you know, so this, I suppose, let me draw a box around Shannon's result. That's where we got to last time, and that's really the, you know, what information theory has to say about entropy, right? Because entropy as the average information content of a distribution, and also as the concept that is, or the expression, this formula that is uniquely constrained by Shannon's axioms. It also, you know, gives you a nice interpretation of the Kullback-Leibler divergence, right, as the expected difference in information, right? HI for the truth minus the HI for the model. Expectation of that over the truth. The true distribution is the KL divergence. Okay, so that's the quick recap of last time. Any questions or thoughts before we move on? Okay, that's a no. So, this is information. Why did I write owl? Information theoretic, I guess. And now we start on a physics journey, but we're but it's a round trip, right? We've walked kind of this path. We're now going to go back to the beginning and walk in a different path, but pretty soon it's going to converge. Something like that. So, there's an idea of entropy as this in physics, as S, where the rate of change of this thing with respect to the internal energy of the system, and let's just talk about ideal gases, because life is easiest in that context. It doesn't mean this doesn't apply to other systems, but it'll just be easiest to work in that place. You know, so if I hold the volume and the number of particles in the gas constant, and consider only the internal energy, so not the gravitational potential energy that the whole thing has because it's in a jar on a shelf or something, but just the you know, no external fields having any effect, just an ideal gas in a container in space somewhere very far from everything. So just that energy, you know, temperature, well, inverse temperature is defined, if you like, by the rate of change of something S with respect to internal energy. Now, to give you an idea of how this arises, I'd like to show you a diagram of the Carnot cycle, and I'm hoping that Dan can take that image and paste it on the next board.
I will try. I may get the wrong image, so this might take 2 attempts, but we'll see.
Okay.
I think that's the right one. You should be able to see it shortly.
Fantastic. I can see it. Okay, so given the time and everything, I let's not dwell here. But the the story is, I mean, to be honest, this is always, I've never felt really comfortable here. Like, I know what engines do. I know how an internal combustion engine works. I know how a steam engine works. And Carnot and others were trying to understand how steam engines worked and make them better and work out how well they could theoretically work. And devised the concepts of thermodynamic reversibility, and the concept of this cycle as the most efficient way to turn heat into work, or vice versa. Clausius, I guess, found. So if I'm just going to go back to the first board and use the space there. So Carnot and others and Clausius, well, ultimately Clausius, leading to Clausius, found that there is some quantity. They found that the change in the internal energy divided by the temperature at a given temperature. So, we're not putting so much energy in that the temperature changes appreciably. There's an infinitesimal change of energy. He discovered that, the integral of that over the cycle is zero. In other words, there's some variable that tracks the point at which the gas in the piston undergoing the Carnot cycle is at as it moves through the cycle. This was before the knowledge of atoms. This was just sort of magic, as far as I can understand, in terms of a kind of scientific discovery. Maybe if I knew more about the history of this, I'd have some idea of how they were able to figure this out. But Clausius named this S. He chose the name entropy, and as a kind of mysterious property that is defined by this. Okay, so we're very far, like we are now sort of here on the journey, if you like, right? We're very far from Shannon's formula. We're also very far from probability distributions and sort of counting anything. So in 2 steps, though, 2 boards probably, we're going to get back to that world. So let's just move over to this board. Okay. And talk about micro and macro states. So, conceptually, and this already we see a link with knowledge, because essentially macro states are what you know, or what is knowable, what you've measured. And microstates, the microstate of the system is all of the details you don't know. All right, so there's a link with knowledge, with information theory, kind of already, at least at a loose level. That's not a cow in meta-uni, is it? Because there aren't any. That's a real one.
You
which
can
is
hear
fantastic.
you can hear the cow. That means my audio settings are incorrect, so that's good. Okay, yeah. Can you still hear me?
Quite. I can still hear you, yes.
Okay, now I can mute successfully, and you won't have to listen to the cow. But I'm glad you pointed that out because it was the audio was coming through the wrong input.
Okay. I was I think I might miss the cow, but that's okay.
It's being fed, so it'll shut up.
So, yeah, it's at some level, this is like known, and this is unknown. But to make it as concrete as possible, because I was always, I remember being a bit mystified by what the concept of a microstate was when I was younger. To make it as concrete as possible, in our ideal gas, there are n point particles. Each one has a position in 3D space, so 3 coordinates, and each one has a momentum. And if you can write down at one instant of time where every particle is and what its momentum is, so in what direction it's moving and how fast, then that is one microstate of the gas. But already you can see that it's a kind of arbitrary distinction, because I mean, it's not an ideal, I mean, no gas is ideal. Even if it's just hydrogen atoms, there's a proton and an electron there. So there's some other stuff, other sort of electron energy level states, and, all sorts of, QCD type gluon stuff happening inside the nucleus, maybe, and all that is there as well, but we're ignoring that. But if we could know that too, I mean, we could choose to include that in the microstate as well. So I would like to, so let's just have in our minds the positions and momenta of all the particles of the gas, and define omega as a function of this internal energy, the volume of the gas, and the number of particles, as the number of microstates compatible with, in other words, sharing the same internal energy, volume, and number of particles. Right, so there are many, many possible microstates in general, but not all of them have the same energy and volume and number of for a given number of particles. The number that do is big omega. And I'm just going to drop I'm going to drop the V and the N and just focus on the E for now. And I'd like to consider a mixture of two gases with total energy big E, and right, so E1 plus E2 equals E. That's the total energy of two gases together. And if I happen to know the macro state of one of the gases, being E1, the energy of the first gas is E1, then, and the energy of the second gas is E2, then I can write down the product, this product of, so this is the total number of microstates compatible with this division of energy between the two gases, E1 and E2. Now, I want to say that actually it's the same type of gas. Like, it doesn't need to be a fundamentally different type of gas. So there's no omega 1 and omega 2 there. It's just omega. It's the same distribution of microstates over energy. And I can write it, of course, like this. V1, given this, that they sum to E. And if I multiply this by some constant C, then I have the probability of finding the two gas, or the mixture with this split of energy. And in equilibrium, I would expect 0 to I would expect this probability to be maximized. Right, so I'm going to differentiate and stick it to equal to 0. So that gives me my constant up front. And then omega of E2 d omega of E1 by dE1. Well, plus omega of E1 d omega of E minus E1 by dE1. Which is equal to that well, minus d omega by dE2, given this of, well, maybe I'll go back to E2, right? And so if I divide both sides by the product of omega of E1 and omega of E2, then I get d by dE1 log omega of E1 is equal to d by E2 log omega of E2 in equilibrium. Right, so there's some quantity beta, which is d by d energy log number of microstates with that energy, which is the same for systems in equilibrium. And you know, if we choose beta equal to 1 over the Boltzmann constant times temperature, and follow Boltzmann and define S as K log omega, then on the left-hand side I have 1 over KT, and on the right-hand side I have 1 over K times ds by dE. So by considering microstates, the microstates compatible with, by considering the probability and the most likely what have we done? We wrote down the probability of a certain split of energy in terms of microstates. And the most probable division led us to this, this quantity, which will lead us to temperature, and made contact with Clausius's definition of entropy. So this is, this one is Boltzmann. It's on his tombstone, Boltzmann, and this one is Clausius. Okay, quick pause for questions and or thoughts before going like one level deeper into microstates and starting to count them. Okay, let's go.
Sorry, where did the log come from just now?
The log came from, so if I divide by omega of E1, omega of E2, omega of E1, omega of E2, then I cancel.
Yeah, right, thanks. Sorry.
Yeah, no problem. Not at all. Yeah. And then it's 1 over, then it's, yeah. There it is. Okay, so continuing the theme of microstates are kind of defined by what we don't know. Let's imagine that we tried to find out, right? So if we do start to measure the positions of the gas particles, if we do start to measure the momenta of them, in other words, if we start to measure the locations of the particles in phase space, then inevitably we have some kind of resolution. And our number of microstates looks something like this. So consider that the total number of particles is big N, which is the sum from I equals 1 to K of Ni, where Ni is the number of particles in the ith position or with the ith momentum or in the ith phase space region, or within the error of the ith measurement, because it always has some kind of error if you're acquiring knowledge through that mechanism. Right? So if there are big N total particles, then I can arrange them in n factorial ways. But if I only care, if I am only able to determine which of the K groups they're in, if you like, then within the group, within the first group, I can make all of those rearrangements and reduce the total number of microstates by that factor. Same for the second group, and so on, until we get to the kth group. Okay, so that's quite a general expression for microstates. It's not specific to an ideal gas or even a gas. Okay, so let's plug that into S over k be equals log omega. Right, and so thanks to Stirling's approximation, which is that the log of a factorial is n log n minus n plus something that goes as log n, right, which is a really good approximation for, I mean, even if it's like, if n is, you know, let's say this is a natural logarithm, but if we just pretend it's a base 10 logarithm for a moment, and if it's like the log of 1,000,000 factorial, you know, so that's that's n is 6. So 6 times log of 6 minus 6. No, sorry, n is 1,000,000. So log n is 6. That's right. So it's like the first term, n log n is 6,000,000 minus 1,000,000, 5,000,000, plus the next term is like 6 relative to 5,000,000. You know, so that's not a bad number of digits to get right, particularly when in typical systems like Avogadro's number is 10 to the 23, right? So 1,000,000 is a small fry compared to realistic values here. Anyway, so we plug in, and the numerator gives us big N log big N minus N, and then the first term in the denominator gives us minus N1 log N1, and then plus N1. Similarly for all others, so let's just do, I already wrote I Freudianly there. I'm just going to write the sum separately because of a cancellation that's going to come up. Right, so that equals n by definition, and so that cancels with that, which is nice. And then let's take a factor of n out front, and we get log, if you don't mind, I'm going to swap the order of terms. So we'll do minus this sum of n I over n log ni, right? And this is the, at least frequency, probability of finding a of what? It's the probability of finding a particle in the ith group, and we'll call that pi. So you can kind of see where we're going. Maybe we're going to get back to Shannon's formula pretty soon. Then I've got a plus log n, but I can throw a sum over pi in there, just as a factor like that, because it's equal to 1. And write this as minus n sum of log of pi multiplied by log ni minus log n. And so we have that S is minus kbn sum of pi log pi, given that pi is ni over n. Compared with h, our hp, which was minus the same sum pi. Well, we were measuring information entropy in bits. so a base 2 logarithm, as opposed to Nats, which we've had to use because of Stirling's approximation. I mean, it's only a constant. There's a different, I guess, Stirling approximation with a base 2 logarithm, but there's only a constant difference. Right, so the constants only determine units. So they don't really matter. Right, so I drew this picture, and I said we're going to head in a different direction, but pretty soon we're going to converge. And I think here was 1 over t equals ds by dE, and we're getting closer over here with s equals k log w and beta equals 1 over kt. But now I think we're pretty much here, right? We've converged with the information theoretic root. That's the physics root, because we have the same formula apart from units. So, how do you feel about that?
It's up to you. What have we got?
So, a thing about that has confused me ever since I heard it for the first time is that this connects a certain definition of information from information theory to something in physics that's based on, well, if we have certain macro information about a system, but don't know certain facts about its microstate, then we get the same thing, which makes sense to me. Both of these are in the end applications of statistics and probabilistic thinking, if you will. But the Carnot cycle thing, and then the laws of thermodynamics that you get out of this, they talk about the actual evolution of physical systems, which, I mean, for this thing here, we have our prior on what we happen to know about the system on the macro level. We know it's, for example, it's total energy and pretty much nothing else. But how do you pull out that this is the kind of prior that is somehow relevant if you want a theory of thermodynamics that predicts the world? Why not some other prior? Like, I don't always know the energy state of a system that I apply the laws of thermodynamics to, yet it continues to obey them anyway.
Yeah, I mean, when you're using the word prior, and we as singular learning theory people and Bayesian inference people, we know what that means in that context. But I don't think but that's maybe a red herring. I mean, I think your question stands. I think your question is, it probes the, like, if you choose different macro variables, do you get a different sort of view of entropy or version of entropy? Do I understand your question?
Well, partially I would say it seems to me a given that you would get a somewhat different entropy. I mean, entropy is dependent on your state of knowledge of the system. What is interesting to me is how apparently some specific choices for the information that we, the observers, have, or macrostate, some priors, correspond to giving you a theory of thermodynamics that seems to be awfully good at predicting things like when stuff turns into gases. And I would assume that some other entropy that derived from some other macrostate that I arbitrarily make up would not do this. And this confuses me somewhat.
Yeah, this is a foundational question in thermodynamics that I wouldn't say has a satisfactory resolution. So Callan's book on thermodynamics, which is the reference. Partly we're going off here, addresses this to some extent, but you can read whole volumes on the sort of underlying philosophical foundations of thermodynamics and not come away feeling this is completely resolved. I can make two remarks. The first is that there aren't arbitrarily many extensive macroscopic quantities that you can choose. Of course, the energy is undefined in some sense because, as Russell was saying earlier, you can choose to pay attention to rest mass or to some other form of energy, right? There is no such thing as the energy. Okay, but maybe you hope to account for all the forms of change in energy that are relevant to the physical processes under consideration. If you don't do that, your theory won't work. If you do, it will. And so it's kind of a statement partly about there are physical processes that we care about in which only certain kinds of changes in energy, like chemical reactions or changes in volume, are present. And as to the kind of extensive quantities that we consider, Callan addresses that in one of the appendices. He talks about symmetry principles, and it's a little bit controversial, I would say, but you can argue that many of the extensive quantities that we consider in the setup somehow have an origin in symmetry principles. Okay, so maybe they're somewhat canonical. And then you can take two foundational attitudes. You can say thermodynamics is founded in statistical mechanics and that you start from like the Boltzmann distribution and work up. Or you can say you start with kind of high-level axioms about observable stuff, which is how Callan would start and how many physicists would think about it. So you set up a system of axioms that say there are these things called extensive quantities, and there's something called the entropy, which has such and such a property. And then you prove that that quantity you called entropy, you derive these formulas that, like the counting microstates here for an ideal gas, you derive this from those high-level principles. But who's to say which kind of founding is correct for thermodynamics? They interact, and which one is somehow the correct view depends partly on what you like. So I think what I'm saying is that I'm not sure that this confusion, if that's the right word for it, that you're expressing really has a satisfactory resolution, at least that I understand.
I think it might correspond.
I suspect it has.
I'm sorry.
I suspect it has one, but oh, sorry.
I tried to say you go ahead.
Okay. Yeah, I suspect it has one, but it would not surprise me if it has yet to be discovered or at least written up in understandable format. Like my guess from this would be from the actual physics side, sort of, there are some very compressed scalar or like just a few variables about the system that, if the system is big enough, determine almost its entire future evolution. And so if you know the state of these variables, you can predict a whole lot about the system. And then sort of the macro state you should choose, and the thing that in your for your information theoretic view of entropy, you should take as known, are like these variables. And then you can make a connection between information theoretic entropy and the thingy that seems to determine when water turns to steam and how much pressure it exerts when it does that.
Yeah, that's correct, except there's a lot of... it's problematic to exactly say what you mean by... I mean, the devil is in this description of the kind of changes that are acceptable in your description, right? There will always be layers of physics. I mean, you could choose to incorporate phenomena into your thermodynamic description, like, I mean, you could look at some kind of entropy to do with the configuration of mass that comes from the gravitational field or something, right? And at what point does that affect the other kinds of physics that you're talking about? It's very hard to draw boundaries there. So I don't know that it can ever be completely clean, but the picture you just sketched is what I would say is how you should think about it.
There is a name for this in statistical mechanics, right? It's ensembles, and what I've used so far is the micro-canonical ensemble, which corresponds to choosing energy, volume, and particle number as the macro states. But if you quite rightly, it's much easier to measure the temperature of a gas, say, rather than its internal energy. And if you allow the energy to vary but the temperature to be fixed, then you have the canonical, I think, ensemble. And there's the grand canonical ensemble and so on, where one of them is one of the macro states is chemical potential, like pressure, but for chemical reactions and so on. And I think this it's only like entropy matching Shannon's formula nicely falls out only of the micro canonical, or at least there are many more states that you need to account for somehow if you let energy fluctuate. Which is why the canonical ensemble is so much bigger than the micro canonical ensemble, this one. And there, I think any sort of state counting approach falls over, and you kind of need to resort to or use the partition function kind of formalism to make any headway.